Well, in the very beginning, I would like to say, well, dear professors and students, good afternoon. Great. I always expect response from my students, as usual. And it's our great honor today to invite Professor Chen to our department to share with us his latest research results. And Dr. Tseng received his bachelor actually in nuclear engineering in National Tsinghua University, but then he started to study medicine in our university, and after that he became a medical doctor in our National Taiwan University Hospital. After a few years practice as a medical doctor, he went to MIT to study advanced MRI technique. So that's very interesting. I mean, he started from nuclear engineering and then became a medical doctor, and then he turned back to nuclear engineering. And he got a PhD in nuclear engineering in MIT, and then stayed 1 year in Harvard as postdoc and as a lecturer. Then he came back to Taiwan in 1999, and now he's affiliated with Center for Optoelectronic Medicine in our university, in the hospital of our university, right? Okay, in the university, sorry. His research interests lie mainly in magnetic resonance imaging for brain and heart. And he recently published a science paper on, he unraveled the neural connection pattern in brain. So I believe he will share with us his latest research result on diffusion MRI. And I would like to remind all of you that he is also a doctor in radiology, so you are more than welcome to consult him about your personal symptom. Any personal issue, you can consult him after the talk. So let's welcome Dr. Tseng.
Good afternoon. It is very happy to be invited here. Physics is always my most favorite subject. In fact, I entered the university when I graduated from high school. My first priority is nuclear engineering. The reason is that I am fascinated by the nuclear physics at that time. So I placed my first priority to nuclear engineering. And at that time, my score of the entrance exam can come to physics department. It's a pity. And after a few years, I decided to switch my career from nuclear engineering to medicine, because at that time I already sense the risk of the nuclear power. So I switched my career at that time. And then I entered the medical school at NTU and finished my medicine. And then I entered the radiology department to be trained as a radiology doctor. And at that time, I first knew about MRI, because MRI was just beginning in early 80s. And at that time, I was a radiologist. And everyone doesn't know what MRI is. So I need to study by myself and learn by myself to understand the principles of MRI and teach others. And at that time, I realized that the research in MRI is very weak in Taiwan. So I decided to go abroad and learn about MRI. And at that time, I only applied one school, that is MIT. And luckily, I entered the MIT program and got my PhD in 1998. And after I got my PhD, I stayed for another 1.5 years. and then I came back in 1999. And so I have been back for 15 years up to now. So today I'm very happy to share with you my works in the past 15 years. Actually, my work is very simple. I basically develop diffusion MRI technique, which is a kind of method in MRI. So today I want to tell you what diffusion MRI is and what, why it is so interesting, especially in medical arena. And also, it is also interesting in neuroscience research. So gradually, in recent years, my direction is a little bit switched toward the brain imaging because I found that, of course, many parts of the body are very interesting, but I found that I need to put all my efforts in the brain research using diffusion MRI technique. So today I'm going to talk about this in my later half of the talk. So this is my brief introduction. So diffusion MRI has a very close relationship with physics, as you already know. Albert Einstein, he first formulated the equation of the diffusion. And as you all already know that diffusion is a phenomenon. So every particle will have a displacement over time. And this is because of the diffusion phenomenon. And actually, Einstein used a function called probability density function, like this. And if we can know the probability density function, the definition of probability density function is it's the probability of a particle at time 0 located at position R. And you will ask a question, what is the probability of this same particle at time delta at position R prime? So this is the probability density function. I think many of you may learn this kind of a probability. And this is just one kind of probability, which is the self-probability density function. So if we know this probability density function, this will works as a kernel to predict any particle or the density function of the particle at time 0. And you can predict this density function at any time points in the future, and also any positions in space. So this is the very key idea of the probability density function. That means we don't need to know the density function for every time point. If we can know the information about probability density function, we can predict this density function at any time point in the future. So this is the key idea. And on the other hand, in the MRI field, it happens that MRI technique called diffusion MRI can detect the diffusion phenomenon. So this is a coincidence. At one hand, we have probability density function, and on the other hand, we have diffusion MRI. And how it works? How does it work? Actually, this is the diffusion power sequence. I won't go into the details, but you all need to know is that this is a RF pulse 90 and 180 degree. And this is the diffusion signal. We call it echo, spin echo. So this is the signal we want to detect. And we also turn on a pair of diffusion gradient. The diffusion gradient is a magnetic gradient, linearly changing its magnitude along a specific direction. This is called diffusion gradient. So we have a pair of diffusion gradients turn on, and the diffusion phenomena of the water molecules can be detected by this kind of a diffusion sequence. As you can know, this gradient actually endows a phase shift or phase turn to each spin, to each proton spins. So here, at different positions, each proton spin will have different phase shift according to the position it is located. So this is an instantaneous application of a diffusion gradient, and you get the phase turn for each diffusion spin. And this is the time interval for spins to diffuse. So after a time interval, big delta, this time interval is called big delta. Here, big delta. So after big delta, we turn on another diffusion gradient, and all the spin, because there is a 180 degree inversion pulse, so all the spins will be flipped to the other side, and you turn on the second diffusion gradient, and the spins will also be endowed by another phase turn, and this phase turn will put them into the final phase. If these spins are not moving, they are all stationary, then this gradient will endow a phase turn, and this gradient will endow the exactly the same phase turn, and so they cancel each other. So at the time of the signal detection, we will get a signal without any difference from the sequence that without diffusion gradients. That means if there is no diffusion, then there's no meaning to place these two diffusion gradients. But of course, water is undergoing diffusion. So actually, the position here and position here are different because of the diffusion. So actually, they will have different phase turns for the same spin, and they will have the phase turns left at the time of signal detection. So here we have the different phases because of the different displacement of these diffusion spins. So we have a kind of Gaussian distribution of the phase turns at the time of signal detection. And here we can see that this diffusion, this phase turn caused by this phase shift will be carried to the diffusion signal, the echo signal. So each spin will have a signal with a phase turn. So this is the diffusion MRI. And so we know that this is the probability density function. And here we can incorporate this probability density function into the diffusion signal. As I just explained, this is the phase turn caused by the diffusion displacement. So this R prime is the position at time big delta, and this R is the position at time 0. So this is the displacement. And here, this is the diffusion gradient strength, and this is the duration of the diffusion gradient. And here we have big delta, this is the diffusion time. So we can formulate this signal by including the probability density function and the phase turn of each spin. And then we do the integral over the space 3D space. And we have double integration over R and R prime. And then we can make the formula simpler by replacing Q with the G. So Q represents the multiplication of gamma delta G. We just replace it as another variable, Q. And then we can also make some changes of the variables. Actually, we change the R prime into capital R. Capital R is the R prime minus R. So we can change the R prime minus R with into capital R. And the equation will become like this. This equation looks more simpler because now you have a simple density function integrated over space. That means that's the average of the density. That is basically a constant. And here we have a probability density function, and exponential is like a phase term and integrate over space. And this looks like a Fourier transform, right? So this looks like a Fourier transform. So here we already see that there is a relationship between the diffusion signal and the probability density function. Actually, diffusion signal is the Fourier transform of the diffusion signal. So this is the surprise. This is the surprise. Diffusion MRI can detect probability density function because they are Fourier pair to each other. So let's work on this first. Here, this S naught is simply this constant. So this means if you don't have any diffusion, then you get the signal like this without any attenuation, any signal attenuation. So this is like a baseline signal. But if you have diffusion and you turn on the diffusion gradient, you will get extra term. This is the extra term. This is the exponential of decay term. This decay actually is the variance of all the phase shifts. So this is like a variance of the phase shift. So this actually is a factor. This factor causes a decay. So signal will be decayed because of the diffusion. So the signal we detect, the diffusion signal we detect, is the attenuation of the S naught. Okay, now we want to apply this concept to the medical image, like the brain. So here I want to illustrate how it works. Now we have this equation. This is the attenuated signal, and this is the baseline signal. Baseline signal, it looks like this. So this is diffusion. This is the brain image without diffusion. Looks like this. But if you turn on diffusion gradient, the image looks like this. So this is the S, and this is the S naught. You can see the difference. So what's the difference? The difference is you can see many regions of the brain have different degree of attenuation because of the diffusion. If you see here, this is the water in the brain. We call ventricles, 脑室, ventricles. It's filled with water. So this is the water in the brain. And you can see here, the signal of the water is all gone. Why? Because in the brain, the diffusion coefficient of the water is the highest. So because the diffusion coefficient is highest, so it attenuates the most. So the signal is virtually black. That means signal is all gone. So because of the high diffusion coefficient, so the signal is all attenuated. And here is the brain This brain actually, the attenuated, the degree of attenuation vary across the, vary from region to region. Some parts of the brain shows less attenuated, like this, a little bit bright. But some part of the region shows more attenuated, like this. So why is that? Why the brain shows different degrees of signal attenuation in the brain? So this is an interesting part. But here I want to show you how we can implement this diffusion attenuation concept into a practical imaging protocol and detect a signal and render this signal in terms of the image. So this is the diffusion-weighted image. Diffusion-weighted image is like this. So more interesting phenomenon can be observed after we get this kind of a diffusion-weighted image. Here we have 3 different images, all the same human brain. And this image is acquired when we apply the diffusion gradient in z direction. Z direction is the direction perpendicular to the screen, okay? And here is the image acquired when we turn on the diffusion gradient in x direction. This is the x direction, right? And this is the image acquired when we turn on the y gradient in this direction, okay? And you can see different, these 3 images have different kinds of diffusion attenuation in the brain. For instance, in the z direction, we can see the most attenuated part is over here. But in x gradient direction, the most attenuated part is over here and here. And in y direction, the most attenuated part is over here, right? So it's very interesting and also confusing why there's different attenuation patterns appeared when we apply different diffusion gradients, okay? I want to say that the first application or the most important value of the diffusion MRI is is to use diffusion MRI to detect stroke, acute stroke, 脑中风. This technique was actually just began in early 90s. And at that time, Dr. Mosley already used it to demonstrate that diffusion MRI is very sensitive to detect acute stroke. So here are 2 images. This is the conventional MRI, and this is the diffusion-weighted image. As you can see here, a part of the brain is all bright up. Why is that? In the conventional image, you don't see too much difference. But in the diffusion-weighted image, you see a very clear bright up region on his, this is actually the right hemisphere. Because in medical term, we look at this as our left side, and this is the right side, okay? We look at the image from bottom to top. So here, actually is the stroke. This is the region where stroke happens. So this is the stroke region. So why stroke region shows signal bright up? Or I can say, on the other hand, why the stroke region doesn't show signal attenuation? Why? Why is that? This is the contralateral healthy side. So you can see the difference. The healthy brain region shows attenuation, but the stroke region doesn't show attenuation. Why is that? Here is an explanation. In words, this is the reason, but I don't want to, I just want you to read, but just listen to my explanation. Because when you got stroke, the cell membrane stopped to work. And cell membrane stopped to work, So some kind of a sodium-potassium pump doesn't work anymore. And then the water will flow into the cell, and doesn't go out. So the cell will become swelling. So many water molecules will get into the cell. And because inside the cell, the diffusion coefficient is lower than the diffusion coefficient outside the cell. Because inside the cell, there are many organelles or many small particles inside the cells. So the diffusion coefficient will be smaller than the diffusion coefficient outside the cell. So if 50% of the cell flush into the inside the cell, the overall diffusion coefficient will be decreased. So that's the reason why the stroke region shows little diffusion attenuation. That's because of the reason I just explained. So you can see this is the most important application of the diffusion MRI. And until today, we still use diffusion-weighted image in the emergency room. When patient sent to the emergency room, doctors suspect that he has stroke. The first reaction is sent to the MRI to do the diffusion-weighted image to make sure that if the patient has stroke. So this is the most important application. But I don't want to say this further because my interest is to use diffusion MRI to many other applications. So let me continue.
So what's the EPI?
Huh?
EPI. What's
EPI.
Yes.
Yeah. EPI is a diffusion sequence. When we implement diffusion-weighted image, we need to use EPI. EPI is echoplanar imaging. And this technique is a must. You need to use EPI to perform diffusion-weighted imaging. And I also I have no time to explain the details about the EPI, but actually EPI is like a carrier to implement diffusion-weighted imaging. So as we just explained, if you have restricted diffusion, like the region in the stroke, the water molecules are restricted inside the cell. So the diffusion coefficient will be smaller, right? So this is the concept. So here, if we look at the normal brain region, there is also some direction dependency of the restriction of the diffusion. For instance, we all know that the brain is many wires, right, in the brain. These are all, there are many neurons and axons. So this is the axons. So we can see water molecules, the diffusion coefficient is less restricted along the direction of the axons and more restricted when it is perpendicular to the axons. So this is called directional dependency of the diffusion restriction. Okay? So actually, not only the stroke region has restricted diffusion. Actually, in the normal brain region, we also have some direction dependency of the restricted diffusion. So this is the crucial concept. So if we want to detect this kind of a directional dependency of the diffusion restriction, how do we do that? Actually, we can model the diffusion as a tensor, diffusion tensor. In the previous slide, I say that Einstein formulate the diffusion as a probability density function, as a kernel, right? And now we make a